Hello and welcome, everyone. Welcome to our talk, Understanding Recomposition Performance Pitfalls. This is Andrei Shikov, I'm Jossi Wolf, and we both work at the Jetpack Compose team at Google, which is very cool. And today we kind of want to talk about common pitfalls around recomposition and performance. So we're going to look at kind of very common things, how to analyze common performance issues and some potential fixes, but most importantly, we're going to talk about compose internals, which is fun. We're going to talk about how does recomposition actually work, and from there, try to build an understanding of why do common performance issues occur and what can we do against them. But before we get into all of the fun, nerdy stuff, let's take a brief second to talk about performance. So I really wanted to have this slide here, like what is performance, but it just didn't fit. One of the most important things when talking about performance is actually understanding that it very much depends on your use case, depends on your app, whether you're building a game, whether you're building a social media app, something with a lot of media, something with a lot of video, or so on. But most importantly, you need to actually recognize whether you are having performance issues. So there's a framework that we really encourage you to follow. We call this Inspect, Improve, and Monitor. And if you've attended Ben Weiss's talk earlier or looked at another performance talk, maybe from ADS, you will know this pattern. So it's really important for you to use tools and not rules to go and inspect your app's performance. Look at things like how long does it take to execute certain parts of your code. And then only then, when you actually notice that there are issues, then you want to improve things. And finally, of course, you want to monitor. You want to make sure that things don't go bad again. But for everything that we're talking about today, we will have assumed that, yes, we have inspected our app, and yes, there actually are issues. And we're not just blindly optimizing our code because we can, because that will lead to bad code over time. So don't do that. There are a couple of related talks here. So there are more performance tips for Jetpack Compose, which is a talk from ADS, which we really would recommend checking out. And then Modern App Performance by Ben Weiss. If you were here an hour ago, congrats. If not, you'll have to wait a couple of weeks. But make sure to check that out. Also, in the line with disclaimers, all of this is assuming that you've inspected and tested your app's performance in release mode with R8 enabled. This is super important for Compose to have applied important optimizations that actually give you the best performance that you can get. But now, let's get to the nerdy stuff. Andrei, you want to clicker?
So, oh yeah, thank you, clicker. So we now understand the performance, and it's time to understand what recomposition is and how it happens. And for that, I chose the most manual of the recompositions that you might see. So it's just text with the clickable assigned to it, and it has a state which increases each time you click on it. And this basically composition somehow figures out the state got updated and just does something like that. And that's where we enter the recomposition loop. It starts when you set content to your activity view, or maybe you like go in raw, so you set it to your composition. And from there, we go through 3 simple steps. One of them is recording the read of the state, then changing the state, where Recomposer figure out that something in the state changed. And the last part, Recomposer knows which state it changed, and it just goes into composition, asks it to update. It's kind of a bit complex thing. Sorry, I forgot the mic. Anyway, it's kind of a bit complex thing, but let's go through all the steps one by one and slow down a little. So again, coming back to our composition, first thing, as I said, was recording the state in a composition. Where does the state read gets recorded? What is the state read? So state read is the access of the state value. It can happen multiple ways, through delegation, like here. It could be just custom getter, or you just call state value directly in a composition. What's important is that it's called as a composable function. And if it's called as a composable function, Compose can just associate this read with the recompose scope. Recompose scope is like an internal structure, which you don't really need to know about if you just develop in usual Compose app. But what's important to know is all restartable functions have kind of the start and the end group, and everything in between will be re-executed over again. So that means that if you read the state here, composition will associate the state read with this exact function. And it will try to remember that for later. We go to the next stage, where we have the state change, something mutated. And this state change got observed by the recomposer. So here, where is the state getting mutated? Well, it's kind of in a really visible place. We click on the text, the touch event gets dispatched, the lambda gets called, and we increase the counter, updating the state value. But to understand what happens inside, we need to go like one state deeper, just like command click through some lines of code that exist in a composed runtime base and find that state is actually observed by the snapshots. So snapshots is a pretty complicated thing, and we won't be going through the whole kind of the whole kind of system here, because it just will take more than 40 minutes that we have for the slot. But the important part to know is state is back with the snapshot system. This snapshot system allows states to be transactional and atomic, and also brings us the observers for reads, for writes, and for applies later. And the last thing is like these observers are used by the recomposer to observe the changes through the snapshot system. And with all of that, it kind of goes around to this, back to this slide. And by the way, if you want to know more about snapshots, Zach Lipasny did an amazing talk on DroidCon NYC this year. I think videos are already available, so you can just watch it through after the conference or after this talk. All right, so now Recomposer knows which state got changed in the last click or whatever the UI frame cycle we had. And we go to the last stage, where Recomposer tells composition, we have this updated state, please update yourself. So what happens here is Composer already knows that a state is shaded with the recompose scope. And there is like this lambda in the end, on the end restart group, which tells recompose scope how to restart this function. This function will be called if the state got changed was associated with this recompose scope. And like in our case, we read the state before, composition did remember that, and the example function got re-executed. So basically, here's the loop of the recomposition. First, we record the state reads while we're executing composables. Then we change state, and this state, through the snapshot system, gets observed by the recomposer, which now knowing which state has changed in the previous frame or so, recomposes composition and updates it to the final state. So we get like this UI as a function of state kind of thing. And this is the most important part to remember for the rest of this talk, because we'll be talking a lot about things how to optimize recomposition, but most of the recompositions are caused by states. So effectively, we'll be talking about how to work around reads and writes of the states in composition. And with that, switching to Jossi.
Yeah, let's talk a bit about some actual practical examples and tips now that we kind of have learned about how recomposition works. So let's take some example code. We have this composable here, and we have a variable scroll offset, which is backed by a mutable state. And then we have a scrollable state. Basically, whenever we scroll, we update our scroll offset with this. And then finally, we have our composables that we call. We have a column. It's just a couple of items. And basically, we want to use the scroll offset to figure out should we show a scroll to top button or not. So we talked about tools earlier, and we haven't really shown you anything yet. So let's look at one of the tools that we have at our disposal. This is called composition tracing or profiling. So you can go and take a look at how long it takes to execute different parts of your code. And you get an actual breakdown of which composables were executed when and how long it took to execute them. So here we see frame 1, everything is great, it's green, that's always good, right? But then frame 2, we see it's red. Okay, warning signal. What is going on? Maybe we have scrolled and we were doing a bunch of work and we see that the frame 2 actually overran. That's not good because we want to have multiple frames, and if we have one frame overrun, maybe we will have to kind of defer some following work, or we have to just skip some following work. And this is what you might perceive as lag, right? If a couple of frames might be skipped, and that occurs often, that doesn't look great on your app. So let's try to figure out what was going on here. We talked about state reads before, and we talked about recomposition happening from state reads. So let's take a look at where we were actually reading state. We can see it's happening here, where we use the scroll offset to figure out should we show this scroll to top button or not. So one of the important things and good things you can do is you can go and you can defer state reads. One approach for that is you can use lambdas. So what we did here, instead of passing scroll offset is bigger than 0f, is we wrap this in a lambda. This lambda just returns an offset, just returns a Boolean when it's invoked. And then we can actually go and use this lambda inside the content composable. So basically what we're doing, we talked about recomposition scopes earlier, and even though you don't really need to know a lot about recomposition scopes, just know that we're able to push down the read as far down in the tree as possible, which is good because then we only really need to redo the work that has anything affected. Now, there are some other optimizations that Compose does, but this is a good technique. So we're reading the state here. One important thing, do not go and pass down a state, a Compose state instead, because that makes your code really hard to maintain over time. Say you just want to try something, you want to hard code a value, and suddenly you'd have to go and produce a state. That's really annoying, makes your code hard to test and change over time. So lambdas are a great way to do this. Now, we've kind of talked about pushing down your state reads in the tree, in composition, but there's actually one thing more that we can do. We can actually go and extract state reads out of composition. So let's remind ourselves of the three phases, the three infamous phases of Compose. Maybe you've heard about them before. We have composition, layout, and draw. Composition being the process of executing your composables and kind of figuring out what things will we need to lay out. Layout being measuring and placement, and draw, well, it's draw. So with that in mind, Compose actually does something very cool. So in our example here, we have the composition, but then we can use, for example, the layout modifier. So the layout modifier, or the layout stage and the draw stage, they each have basically snapshot observers. So basically, they get notified if any state is read in the layout phase or in the draw phase, and then we know, well, this wasn't actually being consumed in composition, so we don't actually need to redo composition. We can just redo layout, or we can just redo draw, which is great, because it lets us skip a bunch of work. So that's awesome. So if we take all of these things, into account, and we kind of go and push our state reads either down in the tree or remove them completely from composition, what we'll see is we'll actually be doing a bunch of less work, which is great. So you can use the layout modifier or the offset modifier, for example, or draw with cache. There are a bunch of them, but kind of go and look out for your phases. And now let's talk about derived states.
Yep. So we talk a lot about how to kind of extract states somewhere from the function. But what if we want to use the state in a function? Returning to our previous example where we had the scroll offset, and we use it directly in a composition with a state read. Maybe something happens with content. Maybe the API doesn't allow us to kind of modify the content itself. And what we want to do is actually reduce the number of times composition updates, because what we care about is not the actual value of the scroll offset. It's whether it's larger than 0 or not. And for that, we can use derived state of. Then the value of the scroll offset, the show scroll to top, will be calculated out of the composition. And if the value changes, so if scroll offset became 0 all of a sudden, then we will update the composable as well. But we only do it in cases when Boolean changes from true to false or backwards. It's just really useful in cases like that when we only care about frequency, we won't care about updates with the less frequency than the initial value that produces those. Similar things can be applied for lazy layouts if you're talking about indices or visible items info. Things to not do with the derived state is to use the state to figure out the values with the same frequency. So scroll offset update to some value, and we subtract 10 here. And we calculate this value out of the composition, but it will always be changing because scroll offset values are kind of different whenever you scroll, right? But the actual value of this derived scroll offset is used in composition. And that means that it will be updating with the same frequency as the derived scroll offset will. basically, you just don't do anything useful with derived state. What happens here is that it's updating every time scroll offset updated anyway. So we can just calculate these values directly there, or remove all of the calculations in the derived state as we did on the previous slide. And the last thing to consider with the derived state of is the new API we added in 1.3. So if you have nested derived states, sometimes you would notice that it gets updated, like the derived state in the bottom will get updated even though the value from the first derived state didn't change. So we just calculate scroll offset, it's still larger than 0, but at the same time we're kind of updating the derived states at the bottom anyway, recalculating it. And only recomposition still doesn't happen, but we spend in cycles recalculating the bottom derived state. And for that, what you can do is add the mutation policy to the derived state. It will allow exactly this nesting of the derived state in all the cases where you have values which update somehow differently and you use them together. It's a new API in 1.3. It's, I think, already stable, so feel free to use it for your derived states. And the last thing in this section, what I wanted to talk about is the reducing scope of the state updates. We're already talking about pushing the scopes down, but we can also create our own scopes. Let's say that we just added some text offset, which animates based on scroll offset or any other value. So animation, again, it's state reads, state writes, meaning more recomposition of the app itself. We don't want to really recompose the app in this case, because it only affects text, so why should we do additional work? What we can do is to move the text offset in a separate function, separate restartable function, creating its own recomposed scope and making the update kind of more efficient, where it's just constrained to a least small piece where it only will update this text and not anything else. And here, with the offset, you can also use like lambda modifier to make it even more efficient with the measure. One interesting, this transition, wow.
Right? We love magic move.
Yes. Sorry. So the interesting part where that happens in the composed UI library is slots in a button, for example. So if you consider this example that we used in the beginning, but instead of text and clickable, we use button, we'll see that it's actually a lambda, composable lambda there, that creates its own recomposed scope. And that means when we update the counter, we don't update the whole example, we only update where the counter was read. And that means this slot lambda, which is pretty interesting, and I'm pretty sure it's more like wasn't really considered in API design, it more kind of happened like a happy accident. But at the same time, it's just really useful sometimes. Really shows you usefulness of the slot APIs you can use. Right, so the last thing, just to repeat, should you optimize and apply all the tips to all of the state reads, all of the things where you read, write, or compose the state in some case? The answer is no. Don't over-optimize. It will likely just overcomplicate your code and will just come out with some weird construction in there. Composers kind of tries to be performant out of the box with the idiomatic code that you may write. So just focus on the understandable composables, and if you have some performance problems, just profile those. You get like some useful traces with information where the work actually happens. And with that, you can just maybe write a benchmark and optimize the performance out of there.
Another thing that people talk a lot about is stability. So let's switch gears from all of our previous performance tips, and let's take a look at the stability topic. So let's say we have this post column composable. Here in there, we just have a column. As an input, we get a list of posts, a list of model, and then we just want to display all of them with a for each loop. So fine, right? Code is simple enough. And maybe we are running a trace. Frame 1, 2, 3, everything looks great, awesome, it's green, it's good. But then suddenly, frame 4, oh, we're doing a lot of work there. So what is going on? We maybe have changed the input, but we have only changed one thing, really. So why did all of our post-composables here get recomposed? Should they have been, and is there a way to kind of avoid that? So this is what stability is about. Basically, stability in compose is a guarantee or some guarantees to the compiler, to the compose compiler, that tells it, hey, you can actually apply safely some optimizations. So stable types basically follow two sets of rules. Either they are immutable, or if they are actually mutable, they notify the composition about these state changes. So for example, mutable state does exactly that. We learned about this earlier, where state tells composition, hey, something has changed. And then composition can go, OK, yeah, I guess I need to redo some work. And let's look at an example of where that's useful, the stability. So basically, this is what a composable or example composable could compile to. So we'll see that we are starting a group, we're ending a group at the end. But most importantly, I want to put your focus on the parameters changed variable here. So basically, we have some logic there where we figure out, did the inputs actually change? And if we know that everything is stable, we can actually figure this out. We can figure out, did it change or did it not change? And if it's not stable, if it's unstable, we cannot safely know whether the thing's changed. And of course, since we don't want to display any stale data, we're just going to be on the safe side. We're going to re-execute that. So in a sense, stability actually allows us to skip certain work, allows us to skip the execution of a composable function body, which is great. So how do you actually know whether your types are stable or unstable? So number one, make your types immutable or have this observable stability, so use something like compose state. You can look at what compose considers your types as by using the compose compiler metrics. You have to enable those in your Gradle build configuration. And basically, it'll generate a couple of files, among them classes.txt and composables.txt. So in classes.txt, you'll find a list of all of the classes of the module that the compose compiler runs on and what compose has inferred the stability as. So here, say we have our data class model, or it's just a class model. We have a post type, which is immutable, but then we have is-synchronized, which is actually mutable. Not good, because we can see that this makes compose go, oh yeah, is-synchronized, unstable, so the whole class becomes unstable. Now, we can also see that our composable, which we can find in composables.txt, is considered restartable, which is pretty much every composable, but then its input is an unstable model. Okay, not good. What can we do? Well, number one thing we can do is we can change to be immutable. We can see we change to a val, and now our model class is actually considered stable. And another really cool thing that we can see is the composable post function is actually skippable now, not only restartable, and the model input is stable. So this allows us to safely skip this work if we know the thing actually has not changed. And if we go and look at a trace now, we'll see that, oh yeah, actually only the thing that has actually changed will need to be re-executed. And that's great, because it can save us a bunch of time. Now, you should pretty much rely on the compose compiler to do its work and to infer stability, but sometimes there are situations where you just have to be explicit about the stability. So for example, you could have a class that has a mutable field, and you're really, really sure 100% that this field will never, ever get used in composition. In that case, it's fine to say, hey, this is at stable or at immutable, which will tell the compose compiler, yes, this is a stable type. I guarantee this. Also puts a lot of responsibility on you, so don't misuse it. And you can also apply this annotation to interfaces, for example, and then their children will actually be considered stable. Now, that's quite a heavy guarantee to make, because you really have to ensure that all of the implementations are then stable too, but can be a very, very helpful tool. Stability tip number 2, not everything has to be stable. It's fine for some things to be unstable. Let's take a look at our post example here. Oh, it's actually supposed to be post column. Sorry about that. And it would take a list of models and not just a single model. And what we'll see is that compose considers the unstable model of list model, considers it unstable. So why is a list unstable? Well, if you pass in a list in Kotlin, it could well be a mutable list. We actually don't know, right, what it could be. It could be an immutable list, but it could also be mutable, in which case we consider it unstable. So technically, you could go and you could include Kotlin x.collections. You could use immutable lists and kind of like be very explicit about this in all of your definitions, and we'd see that, yes, it actually becomes skippable. Awesome. But if we do that and we go and look at a trace, do you see the difference to the slide just a couple of slides ago? No? Yeah, there is none. Not everything has to be stable, and that's a good thing. Track the data flow in your app and really make sure that you really need things to be stable. You don't always need it to be stable. And just because a function is restartable doesn't mean it actually will be restarted. For example, if the state is not being read in that function. Now, we are going over to your favorite topic.
Lambdas.
Love it.
Yes. So this whole talk actually was inspired by like a Twitter thread I wrote about Lambda some time ago. And it kind of deserves its own section. That's what I think. In this place, talks go from useful performance tips you can apply in your app and like kind of advanced Lambda trivia, which can be also useful to you and maybe clarify some moments, but it's a bit more advanced than the rest. So one thing why we don't really talk about Lambdas as a compositive perspective is just because the details of how we handle those are constantly changing. We optimize them day by day. It's kind of work in progress for us. But I understand that most of you already have Compose apps in production. You want to optimize performance right now. And sometimes Lambdas kind of get in the way with their stability. And here, the rest of the talk will be kind of a primer to understand the Lambdas better. The one thing to know about Lambdas, in particular non-composable, just regular Lambda things that we use in Kotlin, is that they're always stable. So Kotlin compiler just considers they're stable default. There is just in a bunch of types that it considers like Boolean strings, and Lambdas are just up there. The thing that we consider as this Lambda stability is about something else. And to clarify what exactly, let's look at what they compile to. Going into compiler stuff. So I updated the post example from the previous slides to open the post and click. So pretty simple thing that most of you usually do for your composables as well. And here, if we look at what it gets compiled to, we would see that compiler created an anonymous class. Well, it's actually given its name, but it's kind of an anonymous class here, which has a field with the model in it. And then implementation, it also implements the function interface from Kotlin. And on the invoke, on the override of the invoke method, you'll see that it's just body of the Lambda. Pretty simple. But inside the composable, we just create a new instance of that class every time. And that means that every time we go with that function, restart, or like it gets restarted somewhere else, we just re-execute it, we'll create a new instance. And Lambda doesn't have any equals implementation. And that means skippability logic, even though Lambdas are stable, cannot be applied. It's just referential equality by default in JVM, and two instances are never equal to each other unless they override equal method. So what can we do about it? The first thing actually is done away by Kotlin compiler. So let's consider this example. We don't capture anything here, so Lambda just kind of prints click on its own, and it can be compiled into a singleton. This singleton is always the same instance that Kotlin reuses on the call side. And that means, as it's the same instance, we can just kind of rely on the compiler to do its work, and this skippability logic will be always applied. But to be fair, that doesn't solve all the cases. To be fair, in my example, 90% of the Lambdas outright are kind of capturing something. That's kind of the purpose of Lambdas in the first place. And for that, Compose tries to step in and help you a little. Here we capture the model, and you can see like the class get compiled in the same anonymous class. And inside Composable, Compose tries to optimize it a little, but memoizing the Lambda, the class that gets created. And the key for that is the capture, and this optimization could be applied because capture was stable. If the captures were unstable, Compose compiler would just skip that because it doesn't believe unstable values at all. And this is what actually causes the confusion. This is like unstable Lambdas versus stable Lambdas. It's just this type of optimization that Compose compiler does. And it is because captures are really hard to judge for the human. Like, let's consider a similar example, but now I moved everything inside the activity. And when we look into what it gets compiled to, we'll notice that we also captured activity, because now we have to open post, like call the method open post on the activity instance, which maybe makes sense to some of you if you just ever work on a memory trace. You notice how Lambdas just can capture random activities windows and whatnot. And yeah, because the post activity is unstable, as most activities are, in this case, we never apply this optimization, and we'll never skip this function. And we'll kind of go back to square zero, where we were in the beginning before we apply all optimizations to the model, and we'll be re-executing all the posts just because lambda instance is different, which is kind of not great. So the thing to know here is that compile is always smart, but it's always getting smarter. But it's never be as smart as you are. What compiler can do is to be consistent and apply certain optimizations everywhere in the places where it knows it is safe to apply them. But for you, the tip is to kind of keep lambdas in mind if the performance is kind of struggling somewhere and you consider the stability to be the problem here. And if you notice that lambdas are indeed the problem, they get recreated. There are different instances of those. You can remember them with the stable keys, like the captures or anything like that. And we, as a compose team, in our turn, actually working constantly on improving this and making sure the compiler optimizations are making this code more and more efficient in the long run. But again, if you need it right now, that's what you can do.
Brings us to my favorite part of the talk, where I basically go, so all of these things that we told you about, should you care? Should you use them? No, unless maybe you are seeing issues. Don't optimize prematurely. I'm sure pretty much everyone will have heard this quote somewhere. Don't optimize prematurely. Really, it'll make your code hard to maintain. It'll give you just pain. So go inspect and improve and monitor, and don't overly optimize just before. So we talked about a ton of stuff, from how does recomposition work, to some performance tips, to stability, to lambdas. So let's just briefly recap a couple of things here. So number one, to keep in mind, state reads. If you are seeing any performance issues, look out for state reads. Where are you reading your state? Are you reading it in composition? Are you reading it kind of like as far down in the tree as possible? Are you reading it in composition or layout or draw? And can you maybe defer the read to the latest stage, for example, if you're applying an offset or something? Number two, stability. Keep stability in mind. If you are seeing issues, check your hotcode paths for unstable types. Use the compose compiler metrics, and actually measure if any additional stability brings you performance benefits, because maybe it won't. Also, Lambda compiler tries its best. Andrei said this, and the compiler is getting better. Remember with care if you are seeing issues. This is it. We have hopefully not copyrighted XKCD on there. Thank you so much for listening.
It's not.
And I guess we do have a couple of minutes for questions if you want to do Q&A, or you can find us later. What do you think?
Yeah, we can have Q&A now. We have like 10 minutes. So does anybody have any questions? Yeah, see one over there.
Do function references have any consideration on when items are recomposed?
I kind of cut them from the talk a little bit, but because they're kind of the thing that is a bit work in progress. So the difference with the function references, we remember lambdas. They have equal implementation, function references. That's why they're kind of a bit different. But what we did in the compose compiler in the compose runtime recently, we treat function references the same as we do lambdas. So now it kind of will be working as intended, because we had some really gnarly bugs where you just pass the lambda with the on-click, and it calls you back with the previous on-click that you passed for the previous element, and you don't want to have that.
How would you handle if lambda that captures activity is causing us problems with the performance? How would you handle its stability?
Right, so there are multiple things that you can do here. One of them is try to remove this function out of activity, maybe to some kind of, just to have a top level and like some kind of stable class. The other thing is just to remember this lambda, if you notice that it is causing problems. Most of the composables kind of made to be written in the top level things, and like the callbacks they call are kind of usually be different. You can see similar problems with activity with the Mu model, by the way. That's why we usually recommend to kind of propagate callbacks down as lambdas, because lambdas are stable, and if you capture a key as a lambda and just call this lambda inside the on-click, it will be just fine.
Hey there. So
Noticing that we have these unstable marks in the text files, looks like to me that Compose has some information that we as developers not really know about unless we look in the right direction. Have you thought about actually highlighting these errors in the IDE as warnings?
We have. I can get real nerdy about this, but I can tell you that we do have a proof of concept, but we are not sure if it'll ever see the light of day. Just because the stability right now is inferred at a later stage in compilation, so you'd actually need to compile once to know whether a type is stable or unstable. So it doesn't like tell you right away when you're typing. You need to compile first. That's a lot of work to be doing while you're working, and we don't want to, take more of your performance. That being said, a way to enable it technically would be to move this analysis kind of like further into the compiler front end. Whether that's completely possible, we're not sure yet, so it might come, but it's something we're aware of. We'd like to have it too. Who knows, someday.
Cool, thank you.
Thank you. If you do have any other questions, find us after. We'll be around the conference and on Twitter. Thank you.